Well, our first Thursday of not only the month but the semester. Obviously, we're getting close to the end of the week and closer to graduating. Fist pump? Yes? We'll be ready when it gets here. Graduation. Okay, so this is where we left off with yesterday. I see on the schedule that tomorrow we have a paper that's scheduled to be handed out. I don't know if we're going to do that yet or not. We'll see how far we get today. But this is where we left off with yesterday. And the idea is you drop the E and then add OIC when you're naming that of acids. Okay, so some of the properties of these, they're quite a bit different than that of inorganic acids. Okay, so I'll give you some examples of those here in just a moment. Because one of the things that we want you to think about when we look at this, for the most part, many organic compounds are nonpolar, whether it's oils, fats, lipids. Any one of those are going to be considered as nonpolar because they are, of course, different organic compounds, but these actually have polar substances to them, and it's because of the hydrogen bonding. And what that means is, one of the things we say, perhaps you might remember physical science, water is the best example of a polar compound because some of those electrons are kind of shared between the oxygen and the hydrogens. Because what do we know about water when it freezes? What does it tend to do? Well, when it freezes, yeah, it expands. That's right. And that's because of the polar bonding that you have in the hydroxy compound, in the O and the H's, okay? What that means is that actually will lower these boiling points. It changes some of the physical properties of this, okay? So that leads into a whole variety of reactions that can happen just because of that concept. Because we consider most organic compounds as being nonpolar, but because of this, okay, the carbonyl group, okay, and the OH group are both polar. Usually we consider, again, all organic compounds as being nonpolar. Okay? Okay, so for instance, what if I read some of these that are found in common foods, okay? We have some propanoic acid, oxalic acid, and citric acid. Now, that alone, probably the citric acid is probably the one that you think really wouldn't be all that bad, and it's not. And what we find them in is one is grapefruit, the other one's lemons, okay? Those two alone, a lot of them contain lots of citric acid, and also vinegar, which is acetic acid, and Swiss cheese contains propanoic acid. And if you want your oxalic acid, be like Popeye. Eat your spinach. Does anyone like spinach? Now, I think for the most part you can get that, I'm not saying in two forms, but if it's in a can, is that where I suppose, is that true? You can get it in a can? I think mostly you get it in like a lettuce type form. I think that's what everyone would agree. You'd rather have it that way than come out of a can where it's, but you can get it that way. Okay. So you're speaking from experience. It's not good. I would agree. Okay. Okay. And I wonder if you lose some of the nutritional value when you cook it. Maybe, yeah. I don't know. Okay. All right. So I want to see where, okay, I want to do this. Okay. This will be the last slide. And one of the reasons I got the book out, because this didn't make much sense to me until I actually read that a little bit. Okay. Oh, okay. Okay, I'll be right with you then. Okay. So again, what makes these compounds polar would be as following, what it says here, okay? So for instance, give me an example. Just keep it simple, like propanoic acid. Yeah, so that being said, how many carbons is that? Okay, so here are, now, you don't have to write this down. Because one of the things, like I said, what may or may not make sense, okay? Because what makes these compounds polar is water can attach, okay? It can reduce this, in other words, break that hydrogen bond, okay? So we can have water branching off of here, okay? 2 hydrogens. That's what it says with the first one, okay? Then we can also, if that wants to stay there, which is fine, we can also have water branch off of here, okay? That's the second one. And then what it's saying is the third one would be off of this one down here, okay? And then that's probably bonding off to something else, okay? So that's what that had meant on that last slide, were the 3 different spots that it can attach. Because what happens is when we do an activity, I don't know if it'll be next week, where it's something that perhaps your great-grandparents used to do at one time, was perhaps make their own soap. I don't think your grandparents would, they might remember their parents, which would be your great-grandparents, talking about that, especially if they lived on a farm. And one of the things that's a common statement about when it comes to pigs is when you're living on the farm, you're going to use everything but the oink. Now, and I think that's kind of funny, because essentially that's true, because when you think of processing a swine or a pig, what's the first thing that comes to your mind besides ham, pork chops, what else? Bacon, okay? I didn't, which one of you two said that? I didn't think you would think of that, but you did, okay? And do you ever look at parts of the bacon? Oh, there's too much fat on that. I don't want that bacon. But that's what makes it good, right? And maybe no one in here likes bacon. Everybody likes bacon, okay? But when you say, yes, the lard, which is something that they would essentially use, I believe, as an acid solution with something called, okay, when someone doesn't tell the truth, okay, we know that that's lie. That's L-I-E. That's a lie. But there's another strong base called lye, which is L-Y-E. And that would be something that you would mix with the lard. And what it does is that jumpstarts, uses as a catalyst to actually create their own soap. And we try to do something similar over in the lab. We would take, is it decanoic acid? Maybe, I'm not quite sure. With an acid, or that is the acid, sorry, with a type of oil and create our own soap. And what that means is you're creating something like a carboxylate salt. And what happens, okay, this is going to be one of the things that's going to be handed out probably next week when we say assign worksheet 1, okay? What happens is if we take an acid, now I need to have different colors here because I think it'll make more sense that way. And we take a strong base, and I wouldn't expect that you would remember that, but maybe you can from last chapter. No, 2 chapters ago, when it came to the aromatics. And perhaps remember a strong base. Sodium something. A strong base. Okay. In that case, it's sodium hydroxide. Okay? Now, what happens here, the reason these are color-coded, okay, and let's make sure I get this right. Is there a catalyst that is needed? And I believe the answer is no. Okay, so when these actually go through and react now, hands aren't big enough. Okay. Actually, I need more. I'm just going to rewrite. It's the same thing. Okay. Tick-tock, tick-tock, tick-tock. Come on, time's a burning. We won't want you to get bored sitting there. Okay, now I can erase that top one. Again, we're just doing the exact same thing. I just wanted more room. Okay. So now, I just want to see what your intuition would look like when, if this is where this breaks apart, which it does, okay? And if this breaks apart, which it does right there, okay? What do you suppose might happen? If this sodium kicks out that hydrogen, which it does, what do we maybe have left over between here and here? Because if those two break apart, okay, and if this sodium replaces that hydrogen, okay, that hydrogen is looking for something to bond with, what is possibly left over from what you reacted that with? And that's so important because we said a lot of these reactions, it's all about what? It's all about the water. So what happens then is this guy is looking for those once that sodium boots it out. So we create what's called a carboxylate salt. And in that case, these are all still here. That carbonyl oxygen is still there. This oxygen is still there. But what happens is this sodium is now attached. Okay? And what do we have left over? Like you correctly said, either HOH or water. Okay? Because this is the first step of understanding how ester formation takes place, because it's something very similar to that. The reason that it's different, okay, is because of what you are reacting that with. It's not saponification, is it? Carboxylate salts would be fine. Yeah, this is a carboxylate salt. Okay. So, can we erase that? Yes. Okay. So, in other words, missed a spot, didn't I? Yep. Okay. Ethanoic acid. What would that be? Ethanoic acid. Okay. 2 carbons. Okay. Our carbonyl group. And okay. Now, when we react that with a strong base, we even do that. Potassium hydroxide. That will react. What would we get on the right-hand side? And go ahead and get caught up. Don't try to do 2 things at once. I'm extremely guilty of that, I know. But I don't know if that's something that's going to happen a year. You're going to have to write fast, look up, write fast, look up. Maybe it's good practice. So this does react. So what do you think we get on the right-hand side? Okay, so these 2 carbons are still here. What else is on these 2 carbons? We'll start with this one. And how many? Okay, all 3. Okay, and I think you said, I just didn't write it down. What about this carbon? Okay,